Hello everyone, I hope you all are doing well. So today I'm here with the CAE interview questions for FE analyst, CA engineer, stress engineer, durability engineer as well. So if you want to know or get into the basics, completely basics of the CAE domain, this video will help you a lot. Okay, you might expect a few questions from this. For sure, we'll be having the questions on theories of failure. So we'll see that one and a few completely basic steps as well. Okay, let's get started with this. First thing, we should know what and all the types are there in CE. Okay, so when it comes to CE, we have the finite element analysis, FEA, right? We have the CFD, computational fluid dynamics, where the Navier-Stokes equations are used. MBD analysis, the multi-body dynamics. Okay, very important. Here we're gonna just deal with the multiple rigid and the flexible bodies to deal with the multiple analysis. Okay, and then we have the thermal analysis, separate module. Okay, electromagnetic analysis and the optimization analysis. Here the design optimization and the topology optimization comes into account. Mercedes-Benz and a few other companies are looking for this now because they are doing some like research and development, right? It is meant for that, and it is the topmost company for research and development. So their design optimization as well as the topology optimization needed. So if you are familiar with these all the things, you can able to just get into that particular firm. Well, we'll see in depth about the FEA domain. So we are well versed with these things, right? And we are preparing for the same thing. So when it comes to FEA, we have the static structural analysis. What we're gonna do here, we're gonna find out the FOS, factor of safety test, stress, strain, and displacement results, and then we'll decide our results whether it is fine or not by using these things. The dynamic analysis. So here there are two things: the time based and the frequency based. Okay, the frequency based we have the model analysis, random vibration, harmonic, seismic analysis, and all will come into account. Yep, so model analysis I had told, and then the buckling analysis. So in buckling, linear and non-linear as well. So fatigue analysis, again in that fatigue we have the uniaxial, triaxial, linear and the non-linear fatigue analysis as well. So just dig more into these things if you want to get more knowledge on these analysis. Heat transfer analysis, the basic. Okay, and then the non-linear analysis. Okay, implicit and explicit we can consider here. So these are the types of FE analysis. Remember that if someone asks you can able to tell these things in chart. Well, the types of linear and non-linear dynamic analysis, as I said, when it comes to these things, model analysis, response spectrum, time history, harmonic, random vibration analysis. Okay. Well, the types of non-linear analysis. So we already know these things: the geometric non-linear analysis, the material non-linear analysis. Okay, and we have this contact non-linear analysis as well. Okay, the buckling non-linear, dynamic non-linear. We have seen these. Okay, remember these things. So if you want to know more about these things, so please research about this and do some analysis on these all the domains so that you can have a hands-on experience on these things. Okay, next things, completely basics. What is stress? So we already know this is the restoring force per unit area of the material. So in short, it is the force per unit area. The unit is Pascal, that is Newton per meter square. Okay, we take it as megapascal, gigapascal for Young's modulus, right? So the formula you could see stress, which is equal to F by A, where area A and the F is the restoring force. Sigma is the stress measured in Newton per meter square or Pascal. Okay. Now in the same stress, we need to know the types. So if you are completely basic, like if you are completely into the starting of this FE and CAE, you already know only this as stress and the strain That's all done. So only these things will come into account, and then we'll do the analysis and complete. This we shouldn't do. We should know each and everything about what and all the things are there, how exactly it is going to impact. We need to have the visualization, exactly what is going to happen in that particular partial differential equation, what and all things come into account. We need to know everything. Okay, so when it comes to types of stress, so we have two things. One is the normal stress, we call it as like longitudinal stress and the volumetric stress. And then in the like volumetric stress also we have it, that is known as the hydrostatic stress. I'll explain in depth later. Okay, so in the longitudinal stress we have the tensile stress and the compressive stress. So you could able to see the image here. We have the normal stress, it might be compressive, it might be the tensile as well. Okay, so you can able to refer this tensile in the sense, if you apply the force, if the component, like if it is increased in the length, it is known as the tensile, it reverse as the compressive stress. Okay, so next thing, we have the volumetric stress and the shear stress. Shear stress, first one is the we can consider longitudinal stress, in that the tensile and compressive, and then we have the shear stress, that is different. Okay, and then we have the volumetric stress, this is known as the hydrostatic stress. I'll come back to this. Okay, so when you are going to deal with the triaxial stress analysis, we'll be having the deviatoric stress, in the sense the tension and compression, and the shear as well. Hydrostatic stress, in the sense the volumetric stress, we can call it as, okay, change in the volume. If it is incompressible, no effect. Okay, the shear stress formula, you could able to see this. So very important thing again, when it comes to normal stress, whatever the force you are going to apply, it is perpendicular to the cross sectional area. Can you see, this is the cross sectional area. If you consider, the force application is perpendicular in the normal stress condition. When it comes to shear stress, whatever the force you are applying, okay, that is parallel, sorry, yes, parallel to the cross sectional area. Can you see, this is how it is going to takes place. Remember that. Okay, shear in the sense, you just take the account, no, like if you have the two solid bodies into account, if you just rub it, or if you take your two hands, if you try to just move it, they will face the shear. Okay, the force is like the parallel to the cross sectional area. Well, that is the basics about stress. Okay, in short, compressive, tensile, and the shear stress, and the volumetric stress, complete. And then when it comes to strain, we know the definition, change in length to the original length, right? Again, there are three types in strain. Remember, we just know that, like if you're the basic beginner, we know that only strain, change in length to the unit length, done. But here we have the longitudinal strain, the volumetric strain, and the shear strain, same thing. Okay, remember these things. Now the torsion, it also will come into account. One more thing, people will ask you what and all the different types of failures you're gonna just expect from the component. I think I forgot to take that one into account, where it is okay, first thing is the bending, right? Due to bending it is going to fail, and due to tension and compression, right? And the torsion, remember that these are the main things we need to remember when it comes to material failure. Okay, this is torsion, is a twisting effect of something and a model. Okay, it is just a twisting effect. Okay, well, so you can see the formula for angle of twist, it is TL by GJ. So we had just like mugged up this particular formula during engineering. I did it. Okay, I didn't know anything about these things, we just know the namings. Even still, well, T is the torque, we know, L is the length of the bar, J is the polar moment, and G is the shear modulus. And you could able to see the diagram there, angle of twist. If you consider, you have the shear stress formula, shear strain formula, and the angle of twist formula. Remember this. Okay, well, so next question comes into account, how do we decide the element size and density? Definitely, for sure, this question will come. Let's say you have a model, so what kind of element you're gonna consider? They'll ask, no, how are we gonna respond for this? So you need to remember these things, the five main things. One is the geometry. Okay, the geometry you need to consider whether it is a small or it is a big, or is it a surface or a shell. Depending upon that, we need to select the elements. Analysis type which we are going to conduct, right? The static analysis, or we are going to conduct the uh, CFD analysis. Okay, in the thermal analysis we need to check these things, and then depending upon that we need to select the elements. Okay, for thermal analysis we have the CD elements. Okay, and then when it comes to 3D elements we have the continuum, that is C3D4 and C3D8. And when it comes to a shell element we have the S6 and S8, right? When it comes to beam elements we have the B31 and B32 elements, like that. Depending upon the analysis type and the elements we can consider these things. Okay, and then we have the mesh conversion study. So what exactly we need to do here? So when it comes to mesh convergency we need to run the multiple iterations to check whether the results are changing with respect to the mesh. So if it is constant, if you have the minute variations, then we need to take into account. Very important. The computational source as well. So if your system is of 16 GB RAM or 8 GB RAM and 4 GB RAM, if you want to run the high level meshes into it, it is not possible, but it will give you the error directly. Don't worry about it. You need to consider the computational resources as well. So material properties, very important. Okay, the stiffness and the thermal conductivity, depend upon that we need to take the elements into account. Okay, so in short, geometry, analysis type, mesh convergence, and the computational resources and the material properties are very important for element size and the density. Okay, so yep, so what are the four different types of deformations in the solid? As I said, the first one is the tension and the compression and the bending and the twisting, the distortion. So due to this the deformations will occur in the any of the solid components. Complete. Well, so more circles. So we know we had drawn some circles and all, and we have given the results. We don't know whether we were right or not. They told us to draw the circles, and we have drawn, and we have connected something else, and we have written some, and we have given it right. But when it comes to CAE, we should know each and everything about the Mohr circle. So why it is needed? So it will help you to visualize the relationship between the normal and the shear stresses acting in the various inclined planes. Okay, the maximum shear and the inclined stresses and all, how exactly they are going to vary with respect to the planes, we're gonna get to know that. I'll explain that things in the failure theories. Okay, remember that. Very important for analyzing the visualize the analyzation of the shear stress and the normal stresses acting on the component. In short, what is a shape function? Still everyone faces the issue with this particular shape function. It is nothing but, okay, it is just used to determine the value of the state variable at any point of the element. Okay, based on the values of the state variables on the three node. Again, it is quite confusing. It's nothing but it's the variable at a particular point. If I consider the Gaussian points, they will be like the nodal variables. So that particular value, if you want to just get into account, we need to take the shape functions into account and we need to solve them. Okay, remember that. Well, next question is the center of gravity and the centroid. We have the mass, area, moment, inertia, and the mass moment inertia. You have the formula here. Okay, so first one, when it comes to mass moment of inertia, it is just a measure of resistance offered by a body to change in the angular momentum. Remember that. Okay, mass moment of inertia, mass moment we can consider. So next one is the any kind of moment of inertia is basically a measure of object resistance to the change in its state. The formula is here, you can refer that. Center of gravity, centroid. This question during engineering I had it. I didn't know what exactly it is, but we knew the what exactly it is going to mean, right? When it comes to center of gravity, this is the point where the total weight of the component will act. Centroid, I remember that I said that whatever the complete mass of the component is there, the center of representation of the center of the mass of the component is centroid. I had like mugged up during engineering days. That was the thing what I had mugged up. Okay, so here it referred to the geometrical center of the body. I think same thing. Okay, so again it is the point where the gravitational force act on the body. Yes, this is the center of gravity point where the whole, like, the center of gravity will act on it. Here it is referred to the center of gravity of uniform density of the object. Okay, so it is totally related to the mass of the component. Okay, if you consider the center of point, that is center of mass, so this is where the whole density will be like centroid, like. Yeah, so it is denoted by G, it is denoted by C, and then in simple, it's a physical behavior of the object where a point where all the weight of the object is acting. Remember that. Okay, so next thing is centroid. It is the geometrical behavior of the component. Okay, so when I consider this, it is the center of the measure of amount of geometry. Okay, so for this answer, if I just take any of the component, let's say if I'm just taking the imagination. Okay, if I consider the mouse and if I just try to hold it and try to like balance it on the finger. Okay, so if you could able to balance it at a certain point, that would be the centroid, we can say. So the whole mass is like concentrated on that point, when center of gravity is the this is the point where all the weight of the object will be acting. Okay, at the center exactly will carry it. Okay, if you want the more details, you can just refer the internet and you can cross check about these things. You can even refer the videos for the better understanding. Okay, it is quite confusing for me. Well, so next thing is the failure theory is very important. So I had already explained this failure theory in brief, but here also I would like to introduce. So first thing, we have the failure theories for ductile as well as the brittle materials. For the ductile, we have the Tresca, von Mises, Horsford, and the Gerson theory. When it comes to brittle, we have the Rangine, muscular modified Morse failure theory. Now, very important thing is, so the point of failure for the ductile materials is the yield strength. Remember, for brittle materials, it is the ultimate stress. Okay, so for ductile materials, the failure will occur at the plastic deformation. Okay, so here the brittle material at the point of fracture. You can see this is the thing we need to remember. Exactly here it will directly fail due to the principal stress. For this, it is shear stress. Remember. Stress strain diagram. So this curve is known as the elastic region, and this is the plastic region. From here to here, the complete whatever the straight line, you can see it is like under the Hooke's law. Okay, where the formula is the stress, which is equal to Young's modulus into strain. In short, Young's modulus is equal to stress by strain. Okay, remember that. So if you have the stress and strain values, you can easily find out the Young's modulus in short. So under this region, the Young's modulus will be constant. If you consider the steel, brass or copper, and if you run the analysis to find out the stress values will be equal. Okay, for all, but strain will depend, like the strain will change, deformation will change. Okay, sorry, the deformation will change. Okay, well, now next thing is the Tresca criterion. So what is the Tresca criterion? So this is known as also like the maximum shear stress theory. So here the component will fail due to the maximum shear stress at the yield point. Okay, if the stress is maximum shear stress at that point, no, this will fail. So this is very much applicable for the uniaxial loading condition. So I could able to see the diagram here at the corner, this one, right? So in this theory, we need to remember that the hydrostatic pressure in the sense the only the volumetric stress. Okay, there is no shear stress into it. Okay, it is independent of that, only the maximum shear stress will consider. Okay, so this is the diagram. So again, when it comes to Tresca theory, you could able to, this is the maximum shear stress theory we call it. So as I told, this is the most bulk if you're going to consider. So if you consider the horizontal axis, in this direction the hydrostatic component will act. So this is independent of this, in the sense you won't have the hydrostatic like the pressure stress on this like the in maximum shear stress criteria. When it comes to increase in diabatic stress, in the sense the shear stress, okay, the tension, compression, everything will act along this. If the size of this increases, this will also increases the diameter, remember that. Okay, well, so next thing we have the von Mises yield criteria. So here in short, this theory, this failure will occur due to the maximum distortion energy at the yield point. So this maximum distortion energy is caused by what? Shear stress. So it is linked with the Tresca theory, maximum shear stress theory. You need to remember that. Okay, so when you just implement these two into account, so you'll be having the final formula, that is the sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, sigma 1 minus sigma 3 whole square by 2 whole square root, which is equal to sigma y. Okay, it's fun. And then, so once you consider this, and if you draw the line like this, the elliptical diagram, so this represents the maximum distortion energy, and inside this the Tresca diagram will fit into it. Okay, and then, so what we can say here is the von Mises theory agrees better for the experimental data. When it comes to Tresca theory, it is more encompassed by the von Mises theory. So instead of referring the Tresca, we better go ahead with the maximum von Mises stress. Everywhere we have seen, right? We're gonna consider the maximum von Mises stress for ductile materials and all to access the results. Well, so Tresca is more conservative in failure, and you can able to see there is more conserved inside it, so the results are very minute here. Now the Rankine failure theory, so what it is, so it is for brittle materials. So why it is for brittle materials? We know brittle materials will fail at what? It is for stress, the maximum stress. Okay, it is not for shear. So due to that, we're gonna consider the maximum principal stress reaches the failure at the failure strength of the component. Okay, that is the ultimate strength, simply fracture directly. Okay, as I said, this failure doesn't consider the yield strength, we already know, so it is only dependent on the deviatoric stress. Okay, remember that. So this is the rectangle, you could able to see, no, like this it gonna impact, it is actually a square. Okay, and it is the just representation of the all three, Rankine, Tresca, and the von Mises. So we could able to see these are away, so we can't consider for the brittle, sorry, ductile materials for Rankine failure theory, remember that. Okay, now Hofsword yield criterion. So what it is, so it is the link between both, that is the Tresca and the von Mises theory. So how it is, you could say, you could able to see the formula, sigma 1 minus sigma 2 whole square, not is not whole square, it is a, sigma 2 minus sigma 3 whole square, sorry, whole raised to a, same thing, sigma 1 minus sigma 3, and then by 2, which is equal to square root of a, it's equal to this. So where if you take a is equal to 1, it will represent Tresca. If you take 2, it is von Mises. Okay, so why we consider it is for triaxial stress conditions. Okay, multiple loading conditions. So in Excel you already know, right? We're gonna consider the von Mises stress and even this Tresca. When it comes to Hofsword, we're gonna consider this triaxial stress. What is this Gaussian failure theory? So in short, it gonna have the values for each and everything, that is the hardening rule, equivalent plastic strain, Young's modulus, initial yield stress, everything will be included here. Okay, it will help you to deal with the like the plastic analysis. Okay, for like the ductile components like the porous solids and all, it is very useful for the failure of the uh, very like the plastic components, we can use this. Okay, but we mainly follow Oxford yield criterion, von Mises distortion theory, and the Tresca theory for the ductile materials. Depending upon the need, we can select them. Okay, brittle materials, I had explained this Rankine theory, right? And then you need to remember, when it comes to tension, very less amount of tension is needed to fail for the brittle materials. When it comes to compression, more amount of compression is needed. Due to that, Rankine theory has been introduced with the Morse failure theory. They could able to see the diagram, right? It has increased because the compression needed is more, right? So due to that, but this particular Morse column failure theory, it doesn't follow the practical whatever the numerical data we're gonna getting. It is not approaching for that. So what we have done is to resolve that we have this modified Moore column criteria. Here what exactly happens, we have made some modifications into the Moore's failure theory. This is the Morse column theory, could able to see green. So we have increased this one to follow the experimental datas, getting. So we're gonna use this modified Moore failure theory for the what, duct, not brittle materials, sorry. Okay, well, so this is for hydrostatic pressure. If you're gonna consider the 3D model, you're gonna have it. Okay, if you're going to consider 2D plane stress strain, you're gonna have the 2D models. Okay, so you could able to see it is with respect to hydrostatic axis. This is how it is going to act. Well, so I hope you got to know how exactly we need to answer for failure theories if you got the questions on it, and the basics of stress, strain, and the torsion and the shear stress. What is dielectric stress, what is hydrostatic stress, we have seen, right? The basics, complete modules, and different types of analysis available in CAE domain. Yep, so this particular what it is, I got the session, right? The session will help you to just deal with the basics. If you like it, please do subscribe our channel. Okay, well, that's all about this session, guys. Thank you, stay tuned, bye everyone.